Okay, so recording has started. So let us start. So before we start today's discussion, so last in the last class, one of you have asked this question, like we have discussed about this thing, right? That the op-amp that you are using is mu A741, right? So there was a small question. The question was like, is there any particular rule for naming this IC, right? So regarding this context, this is a small information that I would like to share with you. So basically, there is not any fixed naming system or any nomenclature that way for the ICs or the integrated circuits, but rather there are type of conventional rules that generally different companies follows, and one it has been followed, then next they will name the ICs accordingly. It's a type of follow-up naming. Okay. For example, you can see this is one of the typical example, but remember this is not that this is not the this convention is not always followed. This is one of the way, because you can see here the naming system is only this way, but you can see here the naming is a bit different. So here you can see the first one is prefix. Prefix, this stands for like, for example, there are TMS written. So TMS is the qualified device, means this is the type of, which type of device? Is it a type of experimental device, prototype device, or this qualified device? Which type of device it is? It has been generally been denoted in this way. Then the second number 320, this stands for this device family, right? Which type of family it is, means which way this device has been made. Okay. Then the technology, which type of technology it has been used, right? This is a flash type or some different type. So the flash type, then it will use this. Then different numbering system. This is actually the IC number, means the unique IC number. So here you can see that device can be of different type. Then there can be some information regarding the package. So package means you have always, means I think you have seen during our, I think first class also we have mentioned this IC, right? If you see from the top, IC looks something like this, right? It may be a plastic case IC, right? Then it is this a type of black type of plastic case. You can say, I think you have seen it, right? So depending on the which type of packaging, it may be this plastic type of packaging, or it may be type of metal packaging, right? In case of a and discrete bipolar junction transistor or MOSFET, right? It can be different of different types. So depending on this package type, you can, this information can also be included in the naming. So you can see here, this is 80 pin gain, PN low profile quad flat back. This is the different different type of packaging schemes are there. So depending on that which type of packaging you are using, this information can be given here. Then the other one is this ACE. This ACE information, this gives the temperature range. For example, if it is this ACE, this stands for minus 40 degree, means device, this device can be operated between minus 40 degree, safely operated between minus 40 degree to plus 125 degree. If it is T, then it is minus 40 to 105. If it is Q, it is minus 40 to 125. Right. This is a type of one naming scheme. Whereas you can also see for this 7400 series, 7400 series, you will be using a lot in case of digital electronics, right? So here for this type of ICs, the nomenclature or the naming scheme would be like that, like this. So first one to these two digits, this will indicate the manufacturer, like we have mentioned this mu A741, this mu stands for this Fairchild, right? The 74 stands for this temperature range here. So you can see here for this type of naming scheme, this temperature been indicated by this a single digit, single alphabet, right? S, T or Q. But for this type of naming scheme, the temperature is indicated by this 74 digit, right? Where see, you can see here 74 digits stand for the 0 to 70 degrees. So this is for this commercial use only, right? Whereas if it is 54, like instead of this 74, if it is 54, right? Then again it would be minus 55 degree to 125 degree. This is for the military applications. right? So that way you can indicate like which type of ICs you are using. Then the other thing is that next is this HCT. HCT stands for this logic series. For example, you can see here, this is an subfamily 7400. This is the basic series and many other, right? So then 0404 is the device type of function. This like, there can be like different like we should not go to that much detail. But here what I wanted to say is that there is no fixed naming scheme. But if you see some name, find some IC name, you can Google it and you will be able to see which type of naming scheme it is using, and like what these terms stands for. So typically for this type of naming scheme, manufacturer name, temperature range, then the logic series, okay, which type of logic it is using, then the device type. So this is basically 7404, right? So this IC number is 7404 for this. Then this last one is this B. B is here indicates the package type. So which type of packaging scheme you are using for this IC, right? So I hope this is a small discussion regarding this, the naming of the integrated circuit, and I hope this part is clear to you. If this is clear, then we can start our today's discussion. Okay, so in the last class, we have started our discussion on this inverting amplifier, right? And we have done couple of analysis, and we have found that for inverting amplifier, which is like this, and for this, if you consider this op amp as an ideal op amp means AOD is infinite, right? That means the differential gain is infinite. Somebody has sent something in chat. Okay. Anyway, so who is this? Just a minute. Yeah, Atullo Sharma. Atullo, can you hear me?
Yes, sir. Now I rejoined, so I can hear now.
Okay, so what is that like you wanted to say in the chat box? You have some
Nothing, sir. I
difficulty.
was just asking that if you're audible or not.
Okay, so can you hear me?
Yes, sir.
Okay, great. Okay, so for this inverting amplifier, which here you can see from this, so here we have considered this AOD is infinite because it is an ideal op amp, and considering that we have calculated or try to find the gain of this amplifier, and this gain has come out to be minus R2 by R1, and this minus sign is expected because it is an inverting amplifier, and the gain is R2 by R1. So this R2 by R1 basically the closed loop gain, right? Now here in this today's discussion, what we will do, we will assume that the input resistance, right? Input resistance for this op amp is still infinite. So that is the property of an ideal op amp, that still holds here. But what we will assume that AOD, that is the differential gain, open loop gain of this op amp, is not infinite, but is some finite number, right? So considering that, we will try to find what is the expression of the gain for this amplifier, and from there we will see, so what is the implications of this AOD on the overall gain, and what would be the expected value of AOD, so that we can consider this op amp to be quite close to an ideal op amp. So let's start. So here, if we say like here this is VI, and this is like 0 volt, so this is also expected to be also this is 0 volt, but for the naming convention we are saying it as like V2, which is basically 0, and this one is, we have named it as this V1, this node potential, and this V1 will also be equal to 0 if it is an ideal op amp, means AOD is infinite, but we cannot consider for this analysis V1 equal to 0 because AOD is not infinite. So we have to take this one as V1 and this one as V2. V2 we can say 0, but not V1. Okay. So for this, we can say this there will be a current which is I1. Say this I1 is flowing from this, and this op amp, for this op amp, the input resistance is infinite, so no current can flow inside to this op amp, right? No current can flow inside. So this I1 current has to flow through this R2 only, right? Okay. So considering that, I think we can always write this one as I1 is equal to Vi minus V1 by R1, right? Vi minus V1 by R1, right? And then what will be this I2? Okay, so let us say that this is I2. Then we will try to equate this I1 and I2. What is I2? Then I2, from this to node potential, we can write I2 in terms of this V1 minus V0 by R2, right? Then what is this V0? This V0, right? We can see from here itself, right? V0 is nothing but this AOD into V2 minus V1, right? The AOD is this open loop differential gain of this op amp, right? That way here V2 is equal to 0, that we can clearly see, right? So what we can say from here, that V1, we can write it as V0 minus V0 by AOD, isn't it? Okay. Now we also know this I1 equal to I2, right? This I1 is equal to I2 because no current can flow inside this op amp. So I1 equal to I2. So just let us write this first. This is V1 by R1. This is equal to V1 minus V0 by R2. And now let us try to replace this V1 with this. Okay, the V1 value here. So this is Vi, this is minus, this become plus V0 of AOD divided by R1. This will be equal to, this is again V1, it is minus this AOD V0 by R2, right? So just from here we can see we have a relation between Vi from as of now and V0. So we can take all this V0 in one side and this Vi on the other side, and then try to find what is the expression for this V output by Vi, right? If you do that, right, I am just writing the expression directly here. So it would come something like this, minus R2 by R1 into 1 plus R2 by R1 into 1 by AOD. Or maybe you can do one thing, you can do a cross check. Okay, can you please check and tell me whether can I write from this expression to this expression? Can I write? Could you please check?
Sir,
Hmm.
sir,
Yes.
why have you equated I1 with I2?
Why? Because I1 is this current and this current is equal to 0. No? So this
Sir,
current has to flow this way only. So that
sir,
way
but
I1 would be
this is
equal to
for
I2.
ideal case, right?
Huh?
Sir, the current inside the op amp is zero. Sir, it is for ideal case, right?
Yes, it is for ideal case. So here the non-ideality that we are considering is only AOD is finite. Okay. The other ideal condition, that is this input resistance is finite, input resistance is infinite, that still holds here.
Okay, sir.
Okay.
Yes, sir.
Okay. So could you please check, can I write it from this to this? Please, can you please confirm it quickly?
Yes, sir, it is correct, sir.
Okay, thank you.
Yes, sir.
Now, huh? It's fine, right? Okay. Now
Yes, sir.
say, yes, now say this AOD, if you consider this AOD is very large, say this infinite, okay. And we have to check it, right? Whether for AOD equal close to, I mean, for AOD to be a very high number, whether this gain is really equal to the ideal op-amp gain or not. Means what we have calculated earlier here, that the gain is expected to be minus R2 by R1. So let us check. So if you put this AOD to be infinite, so it is this 1 by infinite, so basically 0. So this term is 0. So that way, this for AOD to be infinite, you see, this V out by Vi, this will be equal to minus R2 by R1 only, right? So that way, this is for, this is, from this expression, you are getting the case of ideal non-inverting amplifier. Sorry, ideal inverting amplifier. We are still in the inverting amplifier case. Now, let me tell you one thing. Say this R2 is equal to 10 times of R1, right? Then for high ideal case, what would be the gain? V output by V input, that is minus 10, right? For ideal case, okay, right? So we say we are not trying to compare for what would be the value of this ideal gain and the practical gain, okay, for different values of AOD, right? So for here, what we are saying is that say R2 is equal to 10 times of R1. Okay, this is fixed for this case. Okay, and say now AOD is a bit higher, say 100. Okay, so if AOD is 100, then what will be the value of this V output by Vi? Can anyone calculate and tell me? If R2 by R1 is equal to 10 and AOD equal to 100, what would be the value of V output by Vi?
Sir, minus 100 by 111.
Yeah, can you give me some value? Means type of, if it is in
Minus
decimal,
9.001.
minus 9.001. Okay,
001.
001. Okay. Then say if we have considered it to be as 1000, if AOD is equal to 1000, then
9.891. 9.89.
9.89. Okay. Say AOD equal to 10,000. Now this time, how much?
9.98.
9.9.
9.
9.99. Okay, I have not calculated, this value. So what you are telling, I am writing it here. So, okay, fine. So from here, you see, for ideal case, the expected gain is to be minus 10, right? But here, when the gain or open loop differential gain of this op-amp is 100, right? We are getting the gain for this non-inverting, for this inverting amplifier to be around minus 9. So here you can see the error is around 10% compared to the ideal case, or deviation is around 10%. Now, when this AOD value is 1000, right, then we are getting 9.89. So that way, if you consider it to be as 9.9, so that way 0.1 is the deviation. So 0.1 out of 10, I think it would be 1%. So the deviation is 1%. Now, if it is 10,000, see, the deviation has further reduced. So that means the higher the value of AOD, that is this value, right, we will be, our analysis would be quite close to that of this ideal op-amp. And for practical case, this AOD value is really quite high. Okay, it should be more than this. It should be more than 10, like 1,000, around 10,000 or even more, right? So in that way, so you can always consider that even though this AOD is not infinite, but our analysis would be quite close to that of ideal op-amp, right? I hope this part is clear to all of you. Now, this kind of analysis can be further extended not only for this type of circuit, inverting amplifier, but for other type of circuits as well. So I do request you to, whenever, if you have understood this part, please consider this AOD to be finite for other op-amp circuits as well, and try to find what would be the deviation compared to its ideal counterpart. Okay. Yes. So if you recall that last time, or even for today, what we have seen, that if this inverting amplifier, even suppose if it is an ideal inverting amplifier, then in that case the gain is equal to minus R2 by R1, right? Okay. Say now if this R1 is equal to, that I think we have discussed it in the last class as well. If this R1 is equal to 50 kilo ohm, so that way R and say the gain we need say 100, right? Then R2 would be 500 kilo ohm, say minus, right? It would be minus. So that way this R2 value is basically 5 mega ohm, right? So if this R1 is suppose for any reason it has to be, you have to fix it to 50 kilo ohm and you need a gain of minus 100, then that way the magnitude of R2 would be very, very high, right? And we have also discussed earlier that incorporating that high value of resistance in any integrated circuit would be always difficult, right, in terms of real estate, because resistance will take larger area to implement. So is there any way by which we can avoid this, right? We will try to get the similar type of gain, means around 100 gain, but we do not want to use R2 to be that high. So for that, one technique is quite popular. That is called, instead of using on single register at R2, use a T network right here. So you can see earlier we have an only one resistance R2 connected between this inverting terminal and this output, but now we have this type of T network, right? And here you can see the currents I have also indicated in this pink color. So say this current is I1, right? The current which is flowing through this, this is an ideal op amp, so no current is flowing through this, right? And we have also considered for this is ideal op amp in every sense, so that means AOD is also infinite. So that way the virtual ground concept also applied, right? That means this potential is virtually connected with this potential. This point is virtually connected with this point. So that means the potential of these 2 points are similar. So if this current is I1, then we have shown this current to be as I2, this current as I3, this current as I4, right? Okay. Now let us see what would be the gain for this case first, and from there we will try to address this issue, this high resistance issue. Okay. So, but before that, let us try to find what is the gain. So for that, let us again do step-by-step analysis. So what is I1? I1 is equal to Vi. This is 0, right? Vi minus 0 by R1. So that way it is Vi by R1, right? And this I1 is current. No current can flow through this. So this I1 current has to flow through this way. So that way I1 would be equal to I2. Fine. Okay. Now, this potential we have to find, okay, because if you do not know this potential, we cannot find this V output. So let us say that this potential is Vx, okay, this node potential. So if this is Vx, then can we write Vx like this? So this Vx is equal to this 0 minus I2 R2. Could you please check? Can I write it like this? Vx equal to, this is the 0 potential, minus I2 R2, because the current is flowing through this, so this plus minus, right? So it is 0 minus the voltage drop across this resistance. So that would give you this Vx. So Vx equal to this much, right?
Sir, have we again taken AOD as infinite?
Okay. I think I have all mentioned this. So here, input op amp is ideal, input resistance infinite, AOD infinite. Okay.
Okay, sir.
Okay. So here you can see this Vx. If we can write Vx like this, then we also can replace this I2 by Vi by R1, right? So we can write it as Vi by R1. Here it is R2. Or to in a good looking manner, we can write it as R2 by R1, right? Okay. Then what is the value of how can we write I4? I4, if it is in this direction, then I4 we can write 0 minus Vx, 0 minus Vx by R4, right? Isn't it?
Yes, sir.
Yes, sir.
Okay, so you should say in between something, otherwise it looks like I am only speaking. Okay, so here it is this Vx by R4. So if you want, you can also replace the value of this Vx here in terms of this Vi and this resistances. So what we are doing basically here, we are replacing this, or we are trying to find these currents, this like I3, I4 in terms of Vi only. That is the actually thing we are trying to do here, right? So that we can now say, uh, okay, okay, can you please tell me that I want to find gain? How should I approach? So to find gain, I need a relation between V output and V input, right? Okay, so what is V output? I can quite easily say V output, or from here, see, from here I can very easily say Vx minus V output, Vx minus V output by R3, right? Vx minus V output by R3. This is equal to I3, right? Now what is I3? This I3 is equal to I2 plus I4, right? Now I2 I can write in terms of Vi. I4 you can also write in terms of this Vi, because here it is Vx, so you can now write Vx in terms of Vi. So that way, this here also you have one Vx. So this expression only this this expression gives you a relation between V output and V input, right? So from here you can easily find the ratio between V output and V input, which is nothing but the gain. So may I request you to find the gain, or to find the expression of gain for this case, and let's see how you are doing. I have told you how to do it, right? So I1, I2 is already related with Vi, no issue in that. I4, I4 we have connected with Vx. Now Vx we know how to write in terms of Vi. So that way we know this I4 value in terms of Vi. We can find I3 value in terms of this Vi as well, because we can relate this Vx with Vi. Right? So we have an expression of between V output and V input. So please do it and tell me quickly. Yeah, please do it and tell me quickly.
Sir, minus 1 by R1 bracket
Minus
R3,
1 by R1 in bracket.
R3 plus R2 plus R2 by R4.
Yeah, looks like similar to that. Okay, anyway, so let us do it. Okay, those who have not done, so please do it with me. So we can, from here, we can write I2 plus I4. This is equal to I3, right? So here, let me write it here again. So, okay, let me write all the steps. So I am now, what I am doing, I am just writing everything in terms of Vx. Okay, and taken all the Vx in one side so that I can replace this Vx in terms of Vi later on. Right. So from here, you can say V output would be equal to R3 minus R2 by R1 Vi into 1 by R2 plus 1 by R3 plus 1 by R4. So V output by Vi, this would be equal to, I would like to keep it R1, R2 by R1 outside. Want to take R3 inside, so that way we will get here this R3 cancel. So we will get this 1 plus this R3 by R2, R3 by R2 plus R3 by R4. Yeah, I think this is correct. So please do a cross check of this gain.
Yes, sir, I got the same.
Okay, so if you have got the same thing, that is very good. Now try to compare
So it will be minus R3 by R1 into 1.
R3, yeah, but I have
Okay, sir.
kept
Okay,
this
okay.
R2 outside and taken R3
Okay, sir.
inside, because because our, for ideal case, or maybe for the earlier case, okay, the earlier case, the gain was what? The gain was this R2 minus R2 by R1, right? We would like to compare this gain and this gain, right? So I have written it like this. Okay, so it is R2 by R1, and in addition to that, you have this, right? So we can
Sir,
find the gain. Huh.
sir, can we apply star delta transformation here?
Will that be helpful?
Sir, we can reduce the T network into the delta one.
Huh. But that, yeah, means will that be helpful? Yeah, you can do the transformation, but will it be helpful in your analysis?
Sir, after that it is simple series parallel case and we can reduce it to previous case.
Okay, then please do it, and maybe in the next class, share your screen and let us know. Okay, that is
Okay,
good.
sir.
Okay, good. Okay, so here the first thing, our first goal is achieved. The first goal was to find the closed loop gain. So we have find the closed loop gain. So if you now compare this closed loop gain with the previous inverting amplifier gain, then we have seen. Then we can see that for the previous case, the gain was only minus R2 by R1, but here with our minus R2 by R1, we have these additional terms, right? Okay. Now, let's say that can we remove this constraint that we need a very high resistance value here, right? For this R2, can we remove that constraint or not? So probably yes, we would be able to remove that constant. And for that, let us say that we will like to have, where is that? We would like to have similar things, means gain should be around minus 100, and R1 value is fixed. We cannot change the value of R1. Let's see for that what are the other combinations with which we can achieve a gain close to this minus 100. So for that, so let me write it here. We cannot change R1. R1 earlier was how much? 50. Okay. So R1 is say 50 kilo ohm. Okay. And R2, let us say R2 equal to R3 as 390 kilo ohm. Okay. And then obviously we need the value of R4 here. Let's say this R4 value is 33 kilo ohm. Okay, if these values are like this, I need a help small from your side. So if these are the values, these resistance values, could you please calculate what would be the gain? Yeah, please tell me the value of the gain that is coming for these combinations of resistances.
Minus 107.78.
Minus
107.78.
0.78. Okay. So you can see our desired gain was around minus 100. So we have achieved slightly higher. Maybe we can just tweak these values a little bit more and try to get a gain which is close to our desired gain. But see, the important thing is see the values of resistances. So here R2, R3 that we are using is 390 kilo ohm. In previous case, it was 5000 kilo ohm, right? And here R4 value is also 33. So if you see these individual resistances that we need to get a gain or closed loop gain of around minus 100 is quite low, right? Compared to the previous this inverting amplifier case. So this issue can be easily solved, right? By using this T network.
Excuse me, sir.
Ah.
Sir, in integrated circuit, we are more concerned about the space, right?
Yes.
So, will the 5000 mega ohm resistor take more space or 3 resistors take more space?
3 resistors with smaller values take lesser space, much less space.
Okay.
Okay. Yeah, that is a good question. Yeah. So next one is the this summing amplifier. So basically, it is nothing but a a adder actually, right? So here the basic circuit configuration looks something like this. So here there are 3 inputs V1, V2, V3. You could have 2, you could have 4, you could have 5. That is up to you. And so basically, you can see if you have considered only one, this case only V1, and consider the circuit like this, then this is nothing but the inverting amplifier, right? That we have discussed. But now we have multiple inputs for this. Then what would be the expected output or V output? Okay, how can we write it? To do that, so let us apply superposition. So when we are applying superposition, so we have to apply one input at a time. Say let's say we have applied only V1. So when we have applied V1, right, then this V2, V3, this would be grounded, right? So V2, V3, these are ground potential, right? Because V1, V2, V3, they have battery, so you have to replace those battery by their internal resistances, which is basically 0. So that way, this two would be grounded, right? Right. Now this is connected. The non-inverting terminal is connected with ground. So use the virtual ground concept. This potential is also 0. That means this potential is 0. This potential is 0. So for this resistance R2 and R3, like both terminal, potential is 0. So no current can flow through R2 and R3, right? So the current can only flow through this R1, and whatever is the current, again, that cannot go inside to this op-amp, right? That cannot go to R2 and R3. So the same current has to flow through this RF only, right? So that way, if I say, right, this current is I1, then the same I1 current will flow through this RF for this case. So from that, it is not difficult to find what will be the output for this case. Let's say that output we denote it as this V01. So this V01 for that case would be equal to minus I1 RF, or you know that what would be this, right? Because now you can, this is nothing but an inverting amplifier, and you know what will be the output of an inverting amplifier, right? So that way you can also directly write V01 would be equal to minus RF by R1 minus RF by R1 into V1, right? Okay. So remember, V01 is the output for the input V1. V01 is the output for input V1. Okay. Now you consider this V2, right? And then say the output would be V02. So V02 similarly can be written as RF by R2 V2, right? Okay. Then if you apply then V3, only V3, so use superposition, then V03 would be equal to minus RF by R3 into V3, right? So here V03 again stands for this V3, and V02 stands for the input V2, right? Then we know the individual outputs for individual inputs, right? Then what will be the total output? Total output would be equal to V01, V02, V03. So quite easy. It is now RF by R1, RF by R2. Because now these things are not still equal, so I have to also write V1, RF by R2, V2, RF by R3, V3, right? So you can see basically what this circuit is doing is basically adding the inputs, right? V1, V2, V3, but these are not actually adding V1, V2, and V3, but these are adding its weighted values, right? For example, the weighted value of this V1 is here RF by R1, then it has been added. So here for this V2, similarly, it is RF by R2. For V3, it is RF by R3. Then it is adding. It is not adding directly, but we can always choose this combination. R2 equal to R3, R1 equal to R2 equal to R3. So if you choose this combination, then the total output can be written as, it is RF by R1 into V1 plus V2 plus V3, right? So as it is an inverting amplifier, it is quite clear from this image. So you can also see the minus sign, negative sign. This is expected. And here you can see it has been this V1, V2, and V3, these three input has been added here. So this is nothing but the summing amplifier. It is not, I don't think it is very difficult. It's quite easy, right? Okay, so far we have discussed this inverting amplifier where the input has been applied at the inverting terminal. But here we have to also discuss this non-inverting amplifier. So for non-inverting amplifier, the input Vi would be applied at this non-inverting terminal. So here you can see the configuration would be something like this. This is the input Vi. Vi has been applied at this positive terminal. However, this negative feedback, so you can see this from output, the one resistance has been connected to the input, and input it is connected at the negative terminal. So it is basically the negative feedback. So this negative feedback should be present because it is a closed loop gain that we are interested in as of now, right? So for this case, and so here after this R1, this there is nothing. So we have this just rounded it, right? Okay. And this signal is being directly fed to this non-inverting terminal. This is another thing you should notice, right? So from here, if we say this as node 1 and this as node 2, then we can write node 1 and node 2 are virtually shorted, right? We have used this.
So here, if we give the input to the non-inverting terminal, will there be any use of R1 and R2? Because no current flows through them.
Okay, let us see that. Okay, what will be the use of this R1 and R2? Okay, right. That is a good question. So here, let us see this. So this node 1 and node 2, obviously from this analysis, previous analysis, we know that they will be in the same potential because it is the ideal op-amp, AOD is infinite, right? So, and the negative feedback would make sure that this two potential is same virtually, but there cannot be any current flow between this node 1 and node 2. Okay. So that way we can say the potential of this node is also Vi, isn't it? So if this potential is Vi, obviously it will try to create some current flow. So let us say this current is I1, the current through this resistor R1, and this current is I2. If it is so, we can write I1 as this Vi by R1 and I2 as Vi minus V0 by R2, right? Okay. So again, these two are current, okay, that are polarity is in opposite direction, but their magnitude would be the same. So if you just simply use here this KCL, right? So we can write then I1 would be equal to minus of, basically I1 plus I2 would be equal to 0. So I1 equal to minus of I2, we can write. So from there we can have this 1 to be equal to V output minus V input by R2, right? So from here, we have to try to find what is this V output by V input from this. Okay, let me do it. Not write the value. Okay, so it is VI. So it is VI R2 would be equal to V0 R1 minus VI R1, right? So take everything together. So it is V output by V input, right? That would give here R2 plus this R1 divided by this R1. So basically it is 1 plus R2 by R1, right? So you see the gain which is coming out for this particular non-inverting amplifier is something like this: 1 plus R2 by R1, right? First thing is this is the non-inverting amplifier, so the gain is expected to be positive. That is true. That also you can see from here. So gain is positive, right? And one more thing, if you now try to compare this gain with for the non-inverting amplifier gain, for the inverting amplifier gain, for the inverting amplifier the gain was minus R2 by R1, right? But here it is 1 plus R2 by R1, right? So whatever be the value of R2 or R1, you cannot gain for this case a gain whose value is less than 1. So So what I want to mean, this is always
Sir,
huh,
sir, we can put R2 is equal to 0, no?
always one minute, always greater than 1, right? So this value is always greater than 1, right? But whereas for the previous case where we have seen this gain is equal to minus R2 by R1, right? The where here the gain is minus R2 by R1. So here if you choose the R2 value lower than R1, then you will not get any gain, right? However, for this particular case, whatever be the value of R1 and R2, you will get gain at least 1. Yeah, you had a question, so could you please repeat?
Sir, why greater than 1 and why not greater than equal to 1, sir?
Okay, you are right, greater than equal to 1.
Okay,
You
sir.
are right. Fine.
Yes, sir.
Okay, and I think one of you have also had previously one question like why we need R1 and R2 for this case. Is that part clear to you?
Yes, sir.
Okay. So you are right. The gain here is always means gain here is greater than equal to 1 because if you choose the value of R2 say 0, right? If you choose the value of R2 equal to 0, then that basically gives you the gain of 1, right? Yeah, you are right. Okay. And this is the input, right? This is the input here. And if you see from this, so what is the input resistance? Here the input is directly been fed to this op amp. If this op amp is ideal, then if you look from here, this you will see an resistance equal to infinite, means very high resistance, right? So that way we can also say for this case, input resistance is infinite, isn't it? So input resistance is infinite. What will be the output resistance? Again, it's been, you can, if you try to recall, it's an ideal op amp, right? AOD into V of OD, VID, differential gain, right? So if you look from here, again, this is the resistance of this voltage source, which is basically 0, right? So that way the output resistance is 0. So input resistance infinite, output resistance 0. Okay, right. So let me write as output resistance. Okay. Okay. So this is the circuit that which we have discussed just now. This exact circuit I have actually copied this one. So it is R2, R1, VI has been input here. So what are the things that we have seen from here? So gain is equal to 1 plus R2 by R1. Input resistance is infinite. Output resistance 0. This thing we have already seen from this. Now see what would happen if we choose if R2 is equal to 0. So if you make R2 equal to 0 means just short this terminal and this terminal, then what would happen? If you short this terminal and this terminal, what would happen? So it is basically the circuit is like this, right? Okay. Now at that time, what will be the effect of R1? Okay. R1 probably you can choose any value. The other way to look this circuit would be say from this R1 point of view. Say R1 is very high, say infinity. So you just remove R1, right? So if you R1 is infinity, so the gain would be equal to 1 plus some finite value by infinity. If R2 is finite, if R2 is finite, right, then again the gain would be equal to 1, right? If you take R1 to be as infinite, R1 to be finite, so it is 1 plus finite by infinite, so it is basically this part can be neglected, so it is 1, so gain would be equal to 1, right? So in this case also, if you see that this R2, the condition of R2 is R2 only has to be finite. So finite means fine, R2 can be 0 as well, right? Or you can choose any other resistance as well, right? So if this R2 is equal to 0, this circuit will also work fine. So that's also we have seen for the first case. If this R2 is equal to 0 and R1 of this of any value, then the circuit would also work. Right? Okay. So from this, if you do these changes, right? For example, you replace this R1 or remove this R1 to make this R1 to be infinite and this R2 is to be finite, and say this, if this R2 has to be finite, then there is no actually use of taking any register, keeping any register here, just make it short. Right? In that case, the circuit which we will get is this one. And this particular circuit is called the voltage follower or buffer. I think during our discussion on this or this thing, I think one of the problem in the filter section, right, passive filter section, we have come across the buffer, right? So why we need this buffer? Okay, first of all, then, so what is the gain of an buffer? So it is quite clear. The gain of an buffer is equal to 1. Then the question would be, if the gain of the buffer is equal to 1, then why we should use it? So that means input is equal to output or output is equal to input, right? If the gain is equal to 1. Then why at all we need a buffer? The reason behind is these two criteria. The other two criteria. That is, the input resistance is infinite, because if you look again from here, input resistance is infinite and output resistance is 0. If you look from here. Now, let us say at least one example, like how this input resistance infinite would help you, okay, in a particular circuit. So for that, let us say this is a voltage source Vi. This voltage source, even during our discussion on MOSFET and BJT, we have seen all sources will have their internal resistance as well. So let us say this internal resistance of this source is 1 kilo ohm. So it is Ri, right? It is the internal resistance of the source. And with this source, right, you have to drive 1 kilo ohm resistor, which is load, right? Now, what we can do, what are the options you have? First option, you could have directly connect this two, right? If you have directly connected these two and you are interested to look into the output, so what would be the V output for this particular case? So it is Vi, and this is 1 kilo ohm, this is 1 kilo ohm. So V output is obviously equal to 1 by 1 plus 1 into this Vi. So that means Vi by 2, right? Whereas you are expecting that the entire Vi will be fall across this load, which for this particular case, you can see is clearly not happening. This situation would become even worse if you have, suppose Ri equal to 50 kilo ohm, right? The input resistance of the source is increasing. So if it is 50 kilo ohm, then this V output would be equal to 1 plus 1 by 51 of Vi. right? So this particular thing is called the loading effect. Okay, so means when you are adding this load because of this internal resistance of this voltage source, so you are not getting the entire voltage which you are expecting from this source, but rather instead of directly connecting it like this, what we could have done, we could have done something a bit else, something else. So let's say we are not directly connecting this one, but rather now we have introduced here one buffer. Okay, so if you have to introduce one buffer, so we know how buffer looks like. It is positive, it is negative, it has been connected now, and we have to short it out, right? Okay, so what is the resistance, input resistance of this buffer? That is infinite. So that means basically no current can flow through this, right? No current is going to this inside of this op amp. As this no current is going through this op amp, so the voltage drop across this 1 kilo ohm resistance is equal to 0, right? So that means the entire Vi is been applied to this op amp inverting terminal. What is the output from the buffer? Just now we have seen gain is equal to 1. So whatever you will apply, you will get it at the output. So at this output, you will have an voltage of Vi. So now see, if you instead of just connecting directly, if you use a buffer in between, so the loading effect can be eliminated, right? You are getting the entire Vi across this output. So this loading effect can be effectively eliminated by using a buffer circuit. Is this part clear to you?
Sir, no, sir.
Could you please specify which part is not clear?
Sir, how is means the current through this source would be zero, sir?
Because can any current flow inside to this op amp?
No, sir.
So then the current would be what, zero, no?
So, sir, who will means if we are not taking current from the source, sir, means so then what's the purpose of source, sir?
Okay.
Like
So
yes, sir, means it's not
you need
digesting, sir.
what you need is you need this Vi, this source. Okay, you need this Vi, the same voltage here, okay, across this resistance, load resistance, okay, which you are getting from here,
Yes, sir.
right? So that is the sole purpose of this.
And sir,
Or
the means
if
where
you
from where the current will come?
so if you have some difficulty understanding this, you can also think it in this way. So it is 1 kilo ohm resistance, and
Yes, sir.
here this is the internal resistance of this op amp, which is infinite, right? So that way the current value would be almost negligible, but the entire Vi would be dropped across this only. So that way again you can say the voltage drop across this 1 kilo ohm resistance would be negligible. And whatever you are getting across the drop across this op amp, the entire voltage you will be getting at the output side.
Okay, sir. Yes, sir. Now got, sir.
Sir,
Hmm.
sir, what is the need of using input resistance here?
It is not intentional, it will come with the source only. This
Okay,
is not
sir.
an additional one, it will be the means whenever you will use some source, that source has some resistance. Huh?
Hello, sir.
Hmm.
Sir, here we have connected one additional resistance at the output side, right?
Yeah.
But if we try to apply KCL, then I am not getting from where that current will be there, because there is a current flowing
No.
Vi by R2.
Yeah. So it is, you cannot consider this particular op amp as a node. this op-amp you cannot consider as a node, right? Because inside there will be so many transistors, right? Right. So do not consider this op-amp as a particular node. So don't think that current is going from current going to and how the current is. It is not a node. So first thing is that. So op-amp can supply and it can act as a source of current. It can act as a sink for a current. That also we have discussed, right? So
Yes.
this internals from the internal circuitry, the current would be provided to this 1 kilo ohm resistance. Okay, it would not come from this VI.
Yes, sir. Understood.
Hmm. Okay, so far it is good. Okay, now I think so far our discussion was limited to by using only two registers. Now let us now only use only registers, but let us use some other things as well. So for example, let us see what will happen if in this feedback path instead of a register, if we use if we connect one capacitor here, right? Then I think the procedure or the analysis to find this output voltage by input voltage or the what will be the output voltage only, that remains the same. So what we have to do again, see this is at zero potential, so virtual short. So this will be also at zero potential. So this VI, you can find the current which is I, and the same current, it cannot go inside, so the same current I would flow through this capacitor. Just relate these two current and you should be able to find like this relation between output and input. So for that, let us see that we are writing it as like I1 and I2. Okay, so then what is I1? It is quite simple. It is VI by R, right? It is VI by R is basically I1. What is I2? I2 is the current which is flowing through the capacitor, right? So the voltage drop across the capacitor would be like this, right? Into plus minus, and there is a particular relation between this current flowing through the capacitor and its voltage, and that is C into dV dt, right? So what is dV dt? dV dt is the voltage drop across this capacitor. So here, what is this V? V is this one, right? This voltage drop across this capacitor. Okay, by the way, are you aware of this equation?
Yes, sir.
Okay, you are aware of. Okay, then that is good. Or if you are not, then no, this is also not difficult. So you see from here, this for capacitor, you can write this Q equal to CV, right? So just take a derivative dq dt, you will get this dv dt, right? What is this dq dt? Rate of change of charge, which is nothing but the current. So current is equal to C into dv dt, right? So this is the thing that we have used here. Okay, this is where from it is coming. So if it is I2 and the current through this I2 is C into dv dt, so this V, how this V is, huh? Ishan, could you please, yeah,
Sorry, sir.
yeah, your microphone was on. Okay, no issue. So here this I2 is equal to C into dV dt, right? Okay. Now what is the relation between this V and this V naught, right? This V, like V naught is equal to minus of this V, right? It is quite easy, right? It is plus minus and this is 0. So this V output would be equal to minus of V. So instead we can write it like this, C or minus C into dV naught dt, isn't it? Now we can always write this thing, I1 equal to I2, which would give us this VI by R would be equal to C dV naught dt. So this is basically the relation and between this output and input, right? But here we can clearly see there is a derivative that like V output is in terms of like derivative with respect to time. So if you try to find what is V output, then V output can be written as minus 1 by RC integration of this VI dt. Fine. Okay. Here we are assuming that initially the capacitor was discharged. If there was a particular capacitor voltage, right, in this direction, plus minus, and if that voltage was VC, if capacitor was charged initially by a voltage VC, right, then V output would be equal to VC minus 1 by RC integration of this di dt. And this is the case where C was discharged initially. Fine. Okay. So
Minus
here,
VC, no, sir?
huh?
V not equal to minus VC. Minus 1
V not equal to minus VC. Will it be minus? Okay. Right. If I consider the VC polarity to be like this, yeah, then it should be minus. Is that it? Otherwise, if this VC would be like this is plus, this is minus, then it would become plus. Yeah, that is depending on the polarity. You know, this sign depends on the polarity, or basically your like polarity or the convention by which you are taking this voltage. Okay, VC. Right. So here, if you see what is the relation between the output voltage and the input voltage, so you can see the output voltage is basically an integration of this input voltage with respect to time, right? So that way you can see basically what we are getting here is an integration, means input is basically getting integrated and that is giving you the output. So this particular circuit is called this integrated circuit, right? Now what will happen if you just interchange this capacitor and resistor? So earlier resistor was here, capacitor was here, now we have interchange. Now what will happen? Nothing will change much. Here again the potential is 0. The current here is say I. So here this current I would be equal to, or maybe let me write it little below and probably use some other color. Say I will use this color. So here this I current, okay, through this capacitor, that we know this can be written as C dVi dt, right? And the same current has to flow through this resistor R, right? So that way V output would be equal to 0 minus I into R, because this I current will flow through this, right? So it is basically I is this, so it is RC dVi dt. So finally what we are getting is this dVi dt, right? So if you look into this equation, so when the output voltage, the expression of output voltage for this circuit, then you can clearly see that output voltage V output is equal to minus RC dVi by dt, right? So basically it you are getting the like like derivative of your input voltage, first order derivative, right? And this circuit is called this differentiator, and it is quite clear from this expression that why it is called differentiator. I hope this part is clear to you. Any doubt? Because it's quite easy, right? It's type of like if you have
Yes, sir.
understood right this part, then this part is quite easy. Okay, then let us also try to introduce a diode here. Okay, and let's see then what will happen if you introduce a diode here. Okay, So again, the for our goal is to find the output voltage. Okay. Again, the procedure is same. Virtual short, potential 0. This current I1, this current I2. All right. This is the procedure, and this we will follow this procedure only always. So then, what would be the value of I1? I1 would be equal to VI by R. Okay, fine. What would be the value of I2? I2, we know the expression of this diode. If the voltage drop across this diode is V, right? Then we know that it is Is exponential of V by Vt minus 1. So this is V. This is this V, right? Now, how this V is related with this V naught? Again, like previous case, we can clearly see this V output is nothing but minus of V, or this V is equal to minus V, right? Whatever way you can see, right? So that way we can write I2 is equal to Is exponential of, this is the diode equation, well-known equation, right? That's what we are using here. So it is minus V naught by Vt minus 1, right? Again, I1 equal to I2, I1 equal to I2. So that way, what we are getting is like this. Vi by R would be this, yes. This would be equal to Is exponential of V minus V naught by Vt minus 1. And we have seen that if this V output or the magnitude, okay, let us say that if this mod of V output is greater than this 3 Vt, then we can neglect minus 1 term, right? This we have used many times in diode. So if we use now neglect this minus 1 term, then it would be like this. Is exponential of minus V naught by Vt. Right, now we have to find what is the value of V naught. So V naught would be equal to minus Vt ln of this Vi by ISR, right? So you see the expression of output voltage for this case. The expression clearly shows that the output voltage is related with the ln function. Output is related with this input voltage by an ln function, right? So which is basically a logarithmic like logarithmic function, right? So that is quite clear. Then from this it is quite clear then why this type of amplifier is called the log amplifier, right?
Sir,
Hmm.
will this restrict VA?
So,
Because
could
if
you
if VA is negative, then the log will not exist.
yes, yes, you are right. Yeah, that is also quite clear from here. Na, see, if this Vi is positive, then only the current can flow, right? Right.
Yes, sir.
If you now make it right, if you make it negative, current cannot flow through this diode in this direction, no?
Yes.
Right. So that is also, but yeah, your point is right. So it should be all positive only.
So it is only amplifying by a factor of log, only the positive half.
Only the positive.
Okay.
Because for this diode to, for this circuit to operate, this V output voltage should be negative, right? Because this is 0, so that way this is 0, so this is connected with the 0 potential, right? This is connected with the 0 potential. So to make this diode forward bias, or to use this expression, this diode has to be forward bias, means this potential has to be negative only.
If we
So,
can,
sir, we will have to check ln of Vi by Is into R. If it is high, then only we can do
Right.
this.
Right. And see, this is an ln function. So with means if you now change Vi, then you will also see there will be a very small change at this output. I think that is quite also clear, because see, this is the change across this potential is 0. Okay, this is the output, and this output is because basically V output is the drop across this diode, right? And you know that drop across this diode will not change much, right? So if you change this Vi also, then the change in output will not be that way, that significant. Now, the next one is the anti-log amplifier, where we have just replaced like this, the position of resistance and this diode, right? Earlier diode was here, now the diode I have connected here. So again, to do similar type of analysis, find current I. So here, or maybe I will use this color is not that way visible. So here again, the analysis would look like the same. So here this current I would be equal to, this is again at 0 potential, virtual ground, right? So the voltage drop across this is now Vi. Okay, again we are neglecting -1 term, so you can directly write Is exponential of this Vi by Vt, right? Okay, now the same current has to flow through this, right? So V output would be equal to minus of I into R. So minus of I means this Is, so it is Is R exponential of this Vi by Vt. So this is the output voltage. So here you can see this output is related with the input by an exponential function. Right. So here for this type of amplifier, you can see as basically a small change in this Vi, right, can lead in quite significant change in this output voltage, because it is an exponential term, and also you can physically see why this should happen, right? So here output voltage is proportionate to this exponential of this Vi by Vt. Right? So this type of amplifier is called this anti-log amplifier. Fine. Okay, so now I think we are in a position to also discuss this part. So this is an analog multiplier. So suppose you have to design one multiplier, means that we multiply the two voltage values, then how we will do that? See, so far from our discussion, we have learned like about log amplifier, anti-log amplifier, summer or summing amplifier, or this like adder, like all these things, right? So it is V1. Let us say that this V1 is first applied to this log amplifier. So after that, what you will get? You will get this log of, actually, basically it will not be a log, it will be an ln, right? So it will be an ln of this V1, and here it is an ln of V2, right? Okay. Now after that, you have used this like adder or the summing amplifier. So basically it is log of V1 plus V2, which will give you this again ln of this V1 V2, right? Then you can use the anti-log amplifier that we have discussed here. So if you use some anti-log amplifier, so that output would be the exponential of this. So exponential and ln, that will cancel out, and finally you will get this V1 and V2. So probably using this type of scheme, so you can have this V1 and V2, which has been multiplied like that. So like that, if you suppose two voltages are given, 2 or 3 voltages are been given, and if you have to suppose design like V1 plus this V1 like V1 V3, right? This type of thing also you can do, right, by using the proper op-amp circuits, isn't it? Okay.
Sir,
Hmm.
sir, how is this adder made?
Adder. Today only we have discussed now. Yeah, this is the adder.
Okay,
Summing
okay, sir.
amplifier is summing amplifier. Okay, so we can sum up, we can multiply, we can do exponential, we can do integration, we can do differentiation. But what about subtraction, right? So probably that we have not discussed so far. So let us discuss that part here. So here, what we are using two inputs like V1 and V2. V1 is connected with the inverting terminal, V2 is connected with the non-inverting terminal, and still you can see the negative feedback is present, right here. And here, V2 is being connected through an resistor here, like through a combination of resistor R3 and R4, right? Okay. So let us now try to find what would be the expression of this output voltage V out. Okay. So again, the procedure or the analysis would be that way similar, but we cannot analyze when both V1 and V2 are present. So we have to use the superposition theorem, and we have to consider when only one node is only one, so only one of the voltage is being applied, and the other one is being replaced by its internal resistance, which is been basically, if you do that, then this other voltage will be replaced by a ground potential. So let us say that initially this only V1 is being applied. Okay. Oh, this part I have. Oh, some part has copied, some of the part has not been copied. Why so? Okay, let me complete this. Right. So okay. Now what we are saying, we say that only V1 is been working here. Superposition. When V1 is active, right? So here, first thing is that there are no voltage sources connected with this inverting terminal, right? Sorry, with the non-inverting terminal. So with this R3 and R4, and you know, with the from this op amp, no current can come out, no current at the input side, no current can goes in, no current can come out. So that way, no current is coming in, no current is coming out. So we can clearly say this potential would be at 0, this node potential. So if this node potential is at 0, then using the virtual short concept, we can also say this node potential is also 0, right? Right. So we can then say like this is basically grounded, right? Then the upper part, then the remaining part of the circuit is basically and nothing but an inverting amplifier, right? And for inverting amplifier, we know what is the gain, right? So for inverting amplifier, so basically then this part, right? This part is nothing but this inverting amplifier, right? With the including this 0, because you can consider this as a ground, right? And for this inverting amplifier, the output voltage would be equal to minus R2 by R1 of this V1. Okay, I have written V1, so let me write it V1. R2 by R1 V1. Right? Okay. Now let us do the analysis for the other case. Okay, I think I will let me create some space here. Okay. So here this output, this, and we will. So here we are using when V2 is active. So when V2 is active, V1 is not there. So basically V1 is grounded, right? Okay. So this V1 is grounded. Now we cannot really say this potential is 0, right? Like earlier, like here it is quite easy. We cannot say it like here. But we can say the potential here and the potential here would be the same. Okay, and see, it is not difficult to find what is the potential here because we know V2, right? We know no current is flowing inside. So we have to just do a simple voltage division and to find what is the node potential here. So say this node potential we're writing at Vx. So this Vx would be equal to R4 by R3 plus R4 into V2, right? The same potential is been applied here. So this is also then Vx, right? Okay. If this is Vx, then we can find what is this output voltage, right? What will be this output voltage? V0. V0 would be equal to, or maybe in the other way. Yes, guys, are you with me or?
Yes.
Okay. Now, yeah, I think I would like to ask you. Please tell me. I have to find the output voltage now for this case when V2 is active. What should I do next?
Sir, Vx equals R1 by R1 plus R2 times V0.
Vx equal to R1. Yeah, please tell me again.
R1 plus
R1 plus
divided by R1 plus R2. No, sir. R1 divided by R1 plus R2.
R1 divided by R1 plus R2, then
Times V0.
Times V0. Okay. So, is this right? Or if it is right, then could you please explain why this is right?
It's non-inverting circuit.
Is a non-inverting. But for non-inverting, whether this Vx should be this potential or this
So
potential?
we can assume that a source of Vx amplitude is connected at the non-inverting terminal, then we will get the similar circuit. So Vx will be this.
Vx would be this. Okay, you were saying
So
that
it's just a
like
voltage division, right?
it's just a voltage division. Okay, so basically you were saying that to have this voltage for an inverting amplifier, what should be the input voltage? From there you are getting it, right?
Yes.
Okay, if it is so, this Vx is this. Yeah, then what next? Yeah, please tell me what next then.
V out equal to 1.
V out equal to
1 plus R2 by R1 into Vx.
1 plus R2 by R1 into Vx.
Yes.
Okay.
And then, sir, yes, sir.
So, no. Yeah, after that, I need a relation between this, V
Sir,
output
put the value of
and V2.
yes, sir.
R4 by R.
R4 by R3. So is this correct? And have all of you have understood this part?
Yes, sir.
Okay. So this is the output voltage when V2 is active, and this is the output voltage when V1 is active, right? So this is that we are doing the superposition. Then finally, the total output. I think I should denote it by some name like this 1 and this 2, right? To avoid any confusion. So it would be equal to V01, V02. Okay, so finally then what we are getting? We are having here V2. We have to write it like V01 and V02. one of the term is minus, so I would like to have this minus term later on. So let us write with the V2 term first. So it is V2 into R4 by R3 plus R4 into R1 plus R2 by R1, basically this term, right, minus R2 by R1 V1, right?
Sir, we can do this using means without using the superposition also, sir.
Okay, so yeah, I will just give me 1 to 2 minutes. Then after that, you explain to me, okay, how you can,
Yes.
what is your plan? Okay, okay. So here output voltage is this one. So here you can clearly see it is it is an expression which consists of both V2 and V1, right? Then if for this case if we say like R4 by R3 is equal to R2 by R1. Okay, this ratio. Okay, R4 by R3 is equal to R2 by R1, right? This if this ratio holds, right, then the output can be written as R2 by R1 V2 minus V1. Yeah, could you please check that for this condition whether this equation reduces to this equation or not? Could you please check?
Yes.
Yes. I think I am waiting for your response.
Yes, sir.
Okay, very good. So if we have this, right, so means we have to choose this R4 by R3. This R4 by R3 is same value as R2 by R1. Then what we will get? We will get output voltage is the difference between these two input voltages. So that way now you can see if you another operation which is an subtraction, like that also you can do using op-amp circuit. Right? So I hope now the term like why it is called operation is quite
Sir,
clear to you. Yeah.
sir, it is coming as V2 minus V1 into R2 by R1.
Is it? But your friends told like this is okay.
Yes, sir, it is that only, sir. R2 by R1 times of V2 minus V1.
Then why your friend is not getting that?
Sir, like on this ratio, R reverse this ratio and apply one's component also, we will get
Right.
that.
Right. Or probably can we also do it like this? Say R2 by R1, let us add to like 1 to both sides, right? 1 plus R3, R4, right? So that way you will get R3, R4 by R3 is equal to this R1 by R1, right? So you have this term. So this is the term, right? So you can see this is just the inverse of this term, right? So that way these two terms would cancel out. So these two terms would cancel out.
Yes,
So
sir.
that
R4 by R3 would remain.
R2 by R3. Then where did I
R4 by
miss?
R3, sir.
R4 in the pink, but R3 in the yellow color. So it's
Uh,
R4 by R3.
yeah. So have I missed something here? Could you please
No, sir.
check?
No, sir, it's correct, sir. So we will have R4 by R3. In the yellow color it's R3 and in the pink color it's R4. So the terms won't cancel in the pink.
Yeah, these two term will can okay. Right. So what will remain? This is the top one is R3 by this one is R2, right? Okay. Do I need another place to check it? Let me see it because now adding some space would be a bit challenging. Yeah, now probably I can create some space here. Yeah. Right. Okay. I think yes, what you told is correct. So it's the R2 plus this. So R2 plus R4. No, I think there is a small mistake I have done. No. Okay, let me do it again. Like it is R3, R4, R3, R2, R1, R1. Right? Okay. Now we have this term here, right? So instead of this term, what we can write, if this is, let us write the same thing here. And this one we can write it as R3, R4 by R3. So right, we have just replaced this value here. This we have R2 by R1, V1. Okay. Okay. Now after that, so what we can see from here, this part cancels. So it remains with V2, R4, R3, R2 by R1, V1. So it is R3 by R4. R3 by R4 can be also written as R2 by R1. So it is R2 by R1, V2. Here also R2 by R1, V1. So R2 by R1, V2 minus V1. So you can see it, right? Like for this condition, ultimately you will get the output voltage. So this is basically the output voltage. So output voltage, you will get it like this one. Okay. Okay. Fine. Right. Now here. This difference amplifier also, okay, I think one more thing here is important. I think for that also I need some space. Yeah. So another thing which is important here, just then if someone asks like, what would be the input resistance? Now we have applied voltage to both the terminals V1 and V2. So input resistance means if you look from like both, like in from this way, then what would be the input resistance for this difference amplifier? So for that, what you can do, you can probably simply copy it and then paste it there. Do I have that much space? Yes, I have. So I can do it. Right. These two lines will again not be copied. So it's fine. I can bear with that. Yes. Now here, let me do this small update here. This portion was missing. This line was missing. Right. Now what we are trying to find is like what would be this Rin. Right. So to find Rin, what you have to do? Just you have to connect a known voltage source here, say V. Okay. And this voltage source right? And try to find what is the current that is flowing through it. If you know voltage, you know current, you can find what is the resistance, right? That is the way you should, means that is the general way you can find input resistance or output resistance of any circuit. So for this case, you see these R1 and R2, they are in the same potential, right? So this potential and this potential, they are same, they are virtually short, right? That way, it is quite easy to understand that this V would be equal to IR1 plus IR2, right? So that way, V by I would be equal to R1 plus R2. So that way, the input resistance for this case would be equal to R1 plus R2. Okay? But for previous cases, we have seen the input resistance for those amplifiers are generally infinite, right? Because it is the op-amp input resistance. But for this case, what we can see, the input resistance is not quite finite. Input resistance is finite, right? It is basically like R1 this R1 plus R2. That is one thing, right? And the another thing that also probably you have noticed here, that is, okay, what is the gain for the final expression? Yes,
Sir,
this is the gain. Yeah, just a minute. Huh? What is the gain? So from here, this gain is, again, this is the difference gain, but this is the not open loop difference gain. This is the closed loop difference gain. So the closed loop difference gain is R2 by R1, right? So if you need a higher gain, so you have to have an higher R2 by R1 ratio, number one case. And then when you have higher R2 by R1, you should also have, for this criteria to get this equation, you should also have higher value of R4 by R3, right? So that way, the resistance value of R2 and R4, that has to be also higher. And the another point is that the input resistance for this type of amplifier is quite limited. It is R1 plus R2. So if we have this input resistance, then if you want to suppose if you are connecting like here two voltage sources right here, say V1 and V2, and this V1 also have some, it's like, it has some also say the voltage sources have their internal resistances RS, right? Then just now we have earlier we have shown during our discussion of buffer that how this impedance loading effect can impact the voltage across this. The similar situation probably can also arise here for this case, right? So to avoid that, one easy solution that you might suggest is that don't apply V1 directly to this terminal, but use a buffer before that, right? Use a, let's say, like this, say use a buffer before you apply. Okay, the symbol of buffer is this, huh? Use a buffer before this, use a buffer before this. Okay, then the solution, then probably that will solve the loading effect issue. However, that might solve the loading effect issue, you are right. But again, the gain would be limited by this resistances, right? R2 by R1, right? Now, here, if you change the R2, same time you have to also change R4, right? So if you have to change the gain, you have to change the value of the magnitude of resistances for different resistors, not by a single resistor. Okay. So probably in the next class, that is in tomorrow's class, we'll try to see how by using and means how this type of difficulties can be addressed in other type of amplifier, which is called the instrumentation amplifier. Okay. So yes, you had a question, one of you. So could you please?
Sir, I did not understand how you wrote V is equal to IR1 plus IR2. Means VO is 0?
Right. Which VAO you were referring to? Are you still
Yes.
in this analysis, input resistance analysis?
Yes, sir. I did not understand that.
Okay. So input resistance analysis. So for here, what you can do, so apply any known voltage. Okay. Right. And see what is the current that that voltage source is supplying. So you know the voltage because it is a known voltage source. And if you find what is the current, then the ratio of this voltage and current would give you the resistance. Right. So that way, what we have discussed is that as these two nodes are in the same potential, right? So that way we can write that V is equal to I into R1, same potential, plus this I into R3. This is the this K here. This K and from here.
R1 plus it should be R3.
Oh, Okay. Right. Yes, you are right. Right. It should not be R2. How can R2 become here? Right. Because I was referring to, right? Because the same potential and the same current has to like flow through this.
Okay, sir.
Okay. Sorry. This was in my I wanted to mean this R3, but by mistake I have written R2. Okay. So is this part clear to you now?
But I still did not get how we are adding these two.
Which two?
IR1 plus IR3. How can we write that?
Okay. Oh, why can't we write it? You tell me.
Sir,
If you
where are we
consider
applying KV? Means from how are we getting this relation?
this way, in this. Is it clear to you now?
Okay, sir, that V is applied across those two means that is the difference voltage. V.
Okay. So V is here the known voltage. So you can consider it as a different voltage. Whatever V is a known voltage, say 1 volt battery. 1 volt battery you have connected. You see what is the current that is being supplied by the battery. So it is the current and current by voltage, that is basically the internal resistance. You are seeing the internal resistance from here.
Sir, the V that we are using here, it is applied across those two terminals of R1 and R3. Okay,
Yes.
sir.
Yeah, it has been applied to this. This is a known voltage, right? So you can suppose you have a battery, you can attach that battery to between any two terminals. So we have connected it between these two terminals, right? And suppose that battery also have the provision that it shows what is the current that has been supplied by the battery. So you know the voltage, you know the current, right? I'm saying for some practical case, right? Then you can say that means it is quite easy to say at that time, right? The internal resistance that has been seen by this battery is this one. Is this part clear to you now?
Yes, sir.
Okay, then I think then we'll stop here today, and I think the remaining part we will discuss in tomorrow's class and see how far we can do in tomorrow's class. Okay.
Sir,
then we
please
have
upload
left out.
these slides.
Yeah, I will today. I think last 2-3 slides are pending. So I will after this class I will upload it.
Thank you, sir.
Yes, you are welcome. So I think then let us stop here today. So we will again meet tomorrow.
Thank you, sir.
Sir, should we see the output resistance from right side? Then how to find it? I mean, across which terminals should we connect the voltage?
One is this one, the other one is ground. So when you are taking output, you are taking output with respect to always with respect to always ground,
Yes.